All right, so 5.2 Riemann sums. We're actually talking about 5.2c, all right? So this is the back of our paper, and then we'll flip to the front, and then we're going to flip to the back again. So the first part I wanted to talk about was what is sigma notation? So sigma notation, we called it something else. So what we called it in Algebra 2 was summation notation. And that makes more sense to us because we are adding things together. And basically this is telling us to add this function. When we plug in 1 all the way to 100, we're supposed to add up all of those numbers, okay? How does this make sense with the Riemann sum? Well, Riemann sum, if you guys remember, is like, I'll show you this, is like when you take a bunch of rectangles or when you take a bunch of trapezoids and you add them together. So you're adding a whole bunch of things together to get some sort of area. So we can actually write an integral, which is actually an area, right? Because what does the integral represent? It's an area between the function f of x and the x-axis. So we can write an integral as using sigma notation, okay? So if we use the limit, as we have many, like over 1 million rectangles or trapezoids, then that's gonna represent basically what an integral is, which is an area, okay? So I just wanted to show you different ways. Basically, these are different ways that we can find area under a graph. So it says under a graph, but a lot of times, you know, I'm going to say between, because we really want to think between the function and the x-axis, all right? So this one specifically, there's a graph here, and it says, how do you find the area under the graph? Well, what you can do, if you can calculate it, is you can literally find area. So what do I mean by that? I mean, you can break up this function into little parts. So I broke it into a triangle, and then a rectangle, kind of, and then another rectangle. I didn't do a good job with my vertical lines. It was just like weird on the paper, okay? And then a little trapezoid. So in our notes, like in person, we did a little differently, right? So we did like this triangle. We did a square that was a 2 by 2, which is still 4. We did a little square here that's a 1 unit. We did half a square that's 0.5 units. So when we add that all together, oh, by the way, here we have a quarter circle, right? So a quarter of a circle where the radius is 1 is going to be pi 1 squared, and then multiplied by 1/4 is pi over 4. So we can add all of those areas together, and that is exactly the same as when you write it as an integral, because the integral is what represents the area between the function and the x-axis, and the area between is something that we can literally calculate, and we get 7.5 plus pi over 4 units squared, only because it says, you know, find the area, okay? If it says find the integral, like if this was the question, like that, then that would be the answer, all right? So if you were just like, find this, then that would be the answer, 7.5 without a unit squared. But if you're finding an area, technically it's unit squared, all right? So the rest of this backside is just saying, okay, like, let's remind you, you know, we can use left Riemann sums, we can use LRAM, we can use RRAM. If we have many rectangles, we get a better area representation, because these are both like, this is an overestimate and this is an underestimate. So we want it to be as exact as possible. So you can see for these two down here, obviously narrower rectangles are going to give you more rectangles, and it's going to give you a better idea of like the actual area under the curve, between the curve and the x-axis, okay? One thing that we talked about in person today also was, okay, when you look at a rectangle, you know, there's a base and a height. Well, if you think about this base and height on an xy axis, the base is the change in x, right? And then the height, which is a y value, that's our f of x. So that's why the area is going to be the change in x times, so here's the change in x times the height. So height times base, basically, and then right here, this is actually our height, this is actually our base. So we also have in our integral, this is like in terms of x, right? But this is our y value, and this is a bunch of heights from A to B, right? From 0 to 6 or whatever, okay? So we're going to come back to the back of the paper, but first, let's go to the front. Okay, so we did this one together, and we said, how do we do this? What do we do? So you plug 0 in, and you get 1, right? So you plug in 0, you get 1. You plug in 1, you get 3. You plug in 2, you plug in 3. So you plug in 0, 1, 2, 3. So there's 4 terms. So the 0 all the way to the 3 you plug in. And then when you plug it in, you add it all together because this is sigma notation, which is really summation notation. Okay, so we did this. And then you highlighted and then did some underlining. So this is one way we can represent using sigma notation. This is not super popular on the AP test, I will say that, but this is one way. And then what this is basically saying, so this is saying like k equals n, so this is the first term all the way to the nth term. And then this is kind of weird, but this is saying that the partitions, the magnitude of the partitions, so basically the size of the partitions, like the width of the rectangles, okay? The width of the rectangles are really, really small. So if the width of each rectangle is super tiny, close to 0, then you have like a bajillion rectangles. So you basically have an infinite amount of rectangles, and then that's going to give you a really good value. And again, this is a height times a base, because really they're rectangles. Okay, so f of something and then change in x value. And then that's representing the same kind of thing. So this is less popular and more easy. So when we looked at these examples, we said, okay, so, you know, how would that work? I'm gonna go like that. How would that work? Well, this is gonna represent our x, you know, in a function. So this is like x cubed. This says I'm going from 0 to 2 on the x-axis. So 0 to 2, take the integral from 0 to 2 of x cubed. And then this is our change in x. This is in terms of x. So we write it this way, in an integral, okay, as an integral. If I asked you to do this by hand, you'd be like, oh, the antiderivative of x cubed is 1/4 x to the 4th, and then I plug in a 2, and then I plug in a 0, and I subtract, and I get 4. So I didn't ask you to do that, but I do want you to know, like, you can keep going if possible, okay? So for the next one, I'm sure you can just write it in, and you'll be correct, and you're just checking these, right? So from 1 to 9, and then this is basically our x, and then here's our change in x. And the dx is really telling us we're in terms of x. So the 1 and 9 are on the x-axis. That's what the dx is telling us, okay? So just kind of check those. That's what it looks like. All right, so the next part is a little bit more serious, all right? And this is what you'll really see on like an AP test, let's be honest. Okay, so this is what we just had. This makes a little bit more sense because this has to do with n. So we're saying plug in from 1 all the way to basically infinity. Okay, so that's what this is telling us to do. So this like n kind of disappears, and then we're like, oh, just make sure that you're plugging in lots of numbers from 1 to something, and make sure that we're getting close to 0 for our widths, right? So this is height, and this is our base. So make sure our base is getting close to 0 for the size, and that way we have like a bunch of rectangles. This is similar, but it's being more clear, and it's saying, okay, we're going from 1 to n, where n is going towards infinity. So the limit as n approaches infinity of, again, a height and a base. Okay, so then how do we do this? This is written a little bit differently. So let's say, well, actually, we already know the change in base when we did our Riemann sums is b minus a over n, right? So here's a, here's b. And then how do we get our, like, you know, usually this is f of x. So how do we get that x? How do we get, we call it c sub k, all right? How do we get that value? It's going to be whatever this is times k. K equals 1 all the way to infinity, basically, okay? So this times k, and then it's a plus k times whatever that is. So I'm going to give you an example. So we're going to rewrite the integral. We're going to rewrite an integral in this form, okay? So let's say we want to rewrite this in limit of summation form. So we're looking for this kind of value. So I'm always going to have the limit as n approaches infinity of the sum from k equals 1 all the way to n, and then I'm looking for a height and a base. Okay, so this is going to be the form of my final answer. How do we find that final answer? Okay, so number 1, we have to find the change in x. So just like this, we have to find the change in x. Okay, so that's going to be 2 minus 0 over n, which is 2 over n. Number 2, we find basically our x value, but we're calling it c sub k. So our x value is a, which is 0 plus, so a plus, and then whatever we got here times k. So 2k over n. If you put the k on the right side, it's the same thing. It's fine. Okay? So here's our x, or our c sub k value. And then the third part is just, okay, now plug it into the function. What's the function? It's something cubed. So you just do that cubed. And then you fill it in. So here is our function. And then your change in x, again, was 2 over n. So final answer. Okay, so let's try it again for this one. So if you try it one more time, let's see. Did I do step 1? Yeah, step 1, go ahead and subtract. You get 3 over n. Step 2, a is 2, so 2 plus. Step 3, it goes under a root with the minus 3 at the end. So I write that all out. And then I realized, really, that's just like minus 1, right? Because 2 minus 3, I don't want to write that. That's weird. So quantity minus 1. And then we write it as a limit. There we go. Okay, so now you're going to turn to the back, and you're going to do this one. Give it a try. All right? And then I'll show you my answer. So this one, I need to block some things. So I did step 1, step 2, you're not copying me. And then final answer is like that. Yeah? Oh, I wrote that wrong. Ha ha ha. Do you see where I wrote it wrong? So k equals 1 all the way to n, where n goes to infinity. There we go. Okay, that looks better. Okay. So then, this problem, we're going to go backwards, okay? So it's going from our limit to an integral. Okay, so going backwards is definitely tricky. I'm going to write it like this first. I'm going to realize this is my function, and this is my change. So I did this first, but really, like, I do some work over here, but we can ignore it for a second, okay? So you're going to ignore all of this stuff with the little box, and then let me show you. So ignore all of that, and then let me show you. So we do, like, basically 3, 2, 1 instead, okay? So I'm going to start here. I'm going to show you everything, but you're not going to write this stuff yet, okay? So we start with step 3. So step 3 was, okay, this is my function, right? This is my f of x, basically, right in here. So I rewrote that. That means that my x, right, or my c sub k is actually 2k over n. It's the stuff inside, so it's 2k over n. So then I write my step 2, which is c sub k equals a plus something. So c sub k equals this, which is something plus this. So that something must be 0. Right? So a must be 0 in this case, because it's something plus 2k over n, and there's nothing there, so it must be 0. So a equals 0. Okay, I'm going backwards. Now I'm doing this. So then this is supposed to be b minus a over n. I know that this is 2 over n. I know that a is 0, so b has to equal 2. Okay, so now I can fill in from 0 to 2, because I have a equals 0, b equals 2, so from 0 to 2. I know that this is my function in the inside is just c sub k, which is basically like f of x. It's basically x. So I just write x in here. And then in terms of x, so dx. If you do steps 1, 2, and 3 to this, you will get this. I know, it's crazy. So if you do steps 1, 2, and 3 to this one, you would get this original. So when you see something like this, let's say for like multiple choice, I would actually find the easiest one I can for my ABCD or whatever, and then I would actually just do steps 1, 2, 3, because I find that to be easier to go in order, step 1 through 3. And then hopefully it's, you know, what I was looking for. Like, let's say this is choice D or something. I'm like, oh yeah, D works. But if it doesn't, I can just kind of adjust what I'm doing to hopefully find one of those choices that works with the question. Okay? Okay. So the homework was up here. You're doing a quick review 1 through 10, and you're doing these problems, and also A and B using this formula, using that 1, 2, 3 method. Okay? So give it a try. You can do it.